Hello, my name is Kirby and I'm going to discuss today the Sawtooth waveform. How do we do it? How do we generate Sawtooth and its Fourier series with three forms, trigonometric, exponential, and compact trigonometric form for the Fourier series. So let's dive into it. First of all, we're going to discuss what kind of circuit are we going to use to generate the sawtooth waveform. So what I'm going to use is what's called a PUT relaxation oscillator to further uh, explain further what the circuit that I'm going to use is. I'm going to draw it. So there are two main parts to this circuit. One is the constant current source. So we make a voltage divider here. And then the gate of our first PNP transistor is going to be here. Resistor, and then its collector is going, its collector out is directly go to a capacitor, a 10 nanofarad capacitor, and up to the ground. Okay, this is to the ground as well. And then the second part is the PUT oscillator or latches that's going to discharge the capacitor to make this waveform, because the constant current source is going to create this slope. Then the discharge is this fall off from the slope, and that's going to be repeat. So we're going to use PUT latch right here. First is another PNP transistor, and its collector is going to the gate of another of a PNP. No, I mean an NPN transistor. And this NPN transistor's collector is connected to the gate of the transistor right here, and its collector is going straight to the ground. And then another voltage circuit here to latch on this part of the circuit. And then this is going to be supplied by a 9-volt DC source. As you can see, this is called PUT, relaxation circuit. This first and also the transistors here all have a pair of 100, and this is a K, 1K, another 10K, and this too as well. This is a PNP and an NPN, another PNP transistor here, and voltage. So this is the circuit that we're going to use. It's called a PUT relaxation circuit. So I've made a simulation here to display to demonstrate how it works. Okay, so this is called this is the PUT relaxation right here, as you can see. And then this is the waveform, the output. This is the from the capacitor. We're measuring the capacitor in the scope. And from this drawing, we can take we can get the elements of this wave, like the maximum, the mean, the V minimum, and as well as the average. We're going to need those. We're going to need these elements to solve for Fourier series of this waveform. So let's jot it down. First is the Vmax. Vmax, which is equals to 4.8 volts. The V minimum, which is equals to negative 3.5 volts and a V average of 0.7 volts. If we're going to now solve for the series of this waveform. So these are the elements that we got in calculation. Now we're going to solve for the f of t, or the function of the waveform. In this case, let's say that this is a plane, and the sawtooth waveform is kind of slope, right? It's slope. So this is slope. We should have a function for it. And as you know that a slope is equals m is equals to rise over run. We need to figure out the rise and the run of this slope. So in our circuit, or in this waveform, we're going to evaluate it in negative pi to pi. So one period is 2pi, and then its rise is the V peak to peak, or the peak to peak voltage of this waveform. We already have the maximum, then we just need to subtract the minimum to the maximum. And V peak to peak is equals to 4.8 minus 3.5 volts, which is equals to around 8.2 volts. So that's our peak. That's now our rise component. So that's going to be 0.2 volts. So if we compute for the total, if the total function is going, the formula is f of is equals to m, the slope, times time plus the c, or the DC component. Let's call it the DC component. So our DC component is actually DC component is equals to the V average. We're going to prove this in another in our further discussion, further down our discussion rather. So let us finish our function first. First is the slope. So it's going to be V peak to peak, which is 8.2 over our run, or the length, or the x. So it's going to be 2 pi, and then times t plus 0.7 for V average. Okay. So it's going to be around f t is equals to, let's say it is around 1.3 t plus 0.7. So that's the function for one period for the sawtooth waveform, and we're going to get its Fourier series. So let's start with the trigonometric form of the Fourier series of the sawtooth waveform. The general form, or the general formula for the trigo form is, let's call the function u of t, or make of t is equals to a naught, or the DC component summation to infinity from n equals 1, so it's all positive integers, and then the cosine coefficient a sub n, cosine of nt plus b sub n sine of nt. So that is the general formula for the trigo form of the Fourier series. So let's first compute for the three coefficients of each function. Let's start with a naught, or the DC component. A naught is equals 1 over TO, or the initial period, which is in our case 2 pi. So 1 over 2 pi, integral of our interval, negative pi to pi. In this case, we have a symmetric interval. So negative pi to pi, the f of t dt. So we will evaluate this integral with the f of t. So this is this is the derived form, or shall I say, calculated. This is simplified form, and we're going to simplify it further. As you know that the function t right here is odd, and if you integrate an odd function in a symmetric interval, in this case negative pi to pi, it's always equal to 0. So let's prove 1.3 over 2 pi, and then it's going to be 1/2 t squared from negative pi to pi plus So as you can see, it's going to be 0, because this is going to be positive pi because of the square. So it's going to be 0. This function will or this term will cancel out to 0, and what's left is this term, which is going to be around, so it's 0.7 over 2 pi times pi minus negative pi. So it's going to be, so this will become 2 pi, and will cancel out this bottom part with denominator 2 pi. So 0.7 will be our DC component. As you can see, it's the same. The DC, or the V average, will always be our DC component. Now that we have our DC component A naught, we're going to now calculate for the next component, which is A sub n, which is the cosine coefficient, equals to 1 over 2 pi integral of negative pi from negative pi to pi f of t cosine of n t dt. So this is just from the earlier general equation, this part. Let's evaluate it. Let's evaluate this integral with f of t integrated in it. So it's going to be 1.3 t plus 0.7 times cosine of nt dt. there will be similar instances that will happen, like the similar to the last problem or the last component. So it's going to be cosine of nt dt plus this part, which is 0.7 over 2 pi, and it's going to be integral of cosine nt dt. So this will become 0 because, as I've said, any odd function evaluated in the integral and its interval is symmetrical, it will always become 0. Cosine is an even function, and then sin t is an odd function, and then odd function multiplied to an even function is equals to an odd function. So this t cosine nt dt is an odd function, and if we evaluate it to this integral which has a symmetrical interval, it will turn out to 0. So this will become 0, and then this will also become 0 because the integral of cosine nt is 1 over n sine, right? So it's going to be 1 over, so it's 1 over n sine of nt evaluated at negative pi. If we evaluate this, it will turn out to 0 because for all integers, for all integer n, sine will become 0. Sine pi will become 0. So if we integrated, if we included this into the general formula, it will always become 0 because n will always be an integer, as is stated in the condition of general formula. It's n equals 1 to infinity. So all numbers from 1 to infinity, and if you input that number n into this function sine of t, it will become 0. So this will come to 0. So our an now is 0. We have no cosine. We have 0 cosine coefficient, and therefore we have no cosine component in our function. The next part is the b of n, which is the what do you call this? The sine coefficient, and its formula is equals to so next is the cosine coefficient, which is bn. I mean the sine coefficient rather. So the general formula is 1 over pi, integral of pi, negative pi to pi, and once again f of t, sine of nt dt. So we're going to evaluate this integral once again. And then we're going to distribute the sum. So nt dt. So this is the simplified integral, and we're going to solve it now. We can see that this part or this term will become 0 as stated here, right? Because if you once again, if you integrate sine, no, because Select. Okay, let's evaluate this integral. So this will become 0 once again because sine is an odd function. And if you want to this will become cosine, and one is this function will become something like negative 1 over n cosine of n pi minus 1 over n again cosine of negative n pi. And since cosine is an even function, right? So this means that cosine cosine of negative x is still equals to cosine of x, right? So that's how it'll work because it is an even function. So this two will become this term will become positive cosine, and then it will cancel out. So it's still 0. So this is going to be 0, and we're going just to evaluate this term right here. So that will equal to this term will now become let's evaluate this. So we're going to use IBP version the parts in here, and the output will be 1.3 pi. For this part, this is going to be negative 2 pi over n cosine of n pi. So that's the evaluated form of this function using IBP, where u is equals to d is dt, and then dv is equals to sine of nt, and then the v is going to be 1 over sine 1 over n negative cosine of nt. So this is going, if we evaluate this into that, it will turn into this. So the final value for the b of n, or the sine coefficient, is going to multiply these two. So it's going to be negative 2.6. Negative 2.6 cancel out 1, cancel out 2. 1 pi. Actually cancel out 2. So the final form of the sine coefficient will become, so once again this will cancel, so 2.6 over n of cosine of n pi. So that is our sine coefficient. If we want to complete, now we want to complete the full trigonometric Fourier series form. So we're going to call it U of t, or macro t. First up is DC component, which is 0.7, or the A naught plus the summation, starting from n equals 1, which is all positive integers, and then so we're going to have the sine coefficient b of n. Since a of n is 0, we're going to discard the cosine coefficient, right? And now we have the sine coefficient, negative 2.6 over n cosine of n pi, multiply that to our sine function, which is sine of nt. And that is the complete trigo form for the sawtooth wave that we are generating. So if we plug this into our MathCAD, if we plug this in on MathCAD, we'll see that it's exactly the same wave, right? So this is the function. The average is still 0.7, and then that's the output waveform for the trigo. So next up is next we're going to solve for the exponential form of the Fourier series. So this waveform, first is going to write the general equation or general form of this problem, and this time it's going to be from negative infinity to infinity. So we have a negative. So in this form, we will have some what do you call this negative components to the waveform, and we'll have the c of n multiplied by e raised to j and t. So that is the general form for the complex or the exponential form of the Fourier series. First, we'll solve for c of n. Now c of n is equals to 1 over 2 pi, same integral, f of t times e raised to negative j and t dt. So that's the formula for the c of n, and we're going to just input the f of t once again to this formula to evaluate its integral and evaluate its integral. Right? So 2 pi negative pi 2 pi. F of t is 1.3t plus 0.7, and then the exponential function negative j and t dt. Let's simplify further. 1 over 1.3 over 2 pi integral negative pi. For the dc, we distributed the exponential function inside the f of t. So it's going to be e raised to negative j and t dt. Let's put the dt here. Now we're going to evaluate this integral. First off, this will become 0 because this is what do you call this, another sine function. This is the exponential form of the sine function. If we integrate this, the sine function will once again be revealed, or it will come out. So if we integrate this first, it's pi e raised to negative j and t. If we integrate this, what it will result in something like e raised to negative j and t over negative j n evaluated negative pi, evaluated to negative pi to pi, which will result in e raised to negative j and pi minus e raised to negative j, cancel out the negatives, and pi over the denominator, which is negative j n. Now, as you can see, this is forming the shape of like the exponential form of the sine function. So if we just manipulate this term, we're going to get something like negative, so use j and pi minus e raised to negative j and pi over negative jn is to cancel out. And since we know that e raised to j theta minus e raised to negative j theta is equals to 2j sine theta, we're going to manipulate this further. Going to be 2j sine theta over jn, which uh, which we evaluated. Wait, it's in theta form. Let's change it. Sine n pi over jn. So when this is evaluated, it will become 0 for all, or once again, for all integers n, for all positive integers n right here, and also it will become 0. So we're going to neglect this, so it will become 0 now. So now, let's evaluate this. Since this part or this part is the complex sinusoid will always result to 0 if it's evaluated it's evaluated over a full period, and n is not equal to 0. This will always become 0. And then we're just going to evaluate this part next. So we're going to use once again integration by parts, where u is equals to t, du is dt, and then this exponential sinusoid is our dv, and our v is e raised to negative j and t over negative jn. So let's complete the form. D is negative j and t over same denomination. This is the uv. This is to be evaluated in pi to negative, from negative pi to pi, and plus, since this operation will cancel out to minus sine, and then 1 over jn, and then negative pi from pi dt. So we're going to evaluate this. Let's not forget the coefficients, 1 over 3 over 2 pi. Next up is this. Let's see. So it's going to be, so this is going to be 0 once again. It's the same as this. This is a complex sinusoid when you integrate it over a full period where n is not equals to 0. It's always going to be 0 if n is not equals to 0. So let's evaluate this function to negative pi to pi. What will happen next is something like negative jn pi over negative jn minus, now there's going to be a plus because of the jn denominator, or the negative denominator, negative pi e raised to negative j, e raised to negative j and t. Then this is not t, sorry, this is negative pi. Since this is negative and the pi is also negative, this will become now positive jn pi, and the denominator is going to be positive as well, multiplied to the coefficients. Okay, so I think we're going to use the Euler's formula, which is e raised to negative j and pi equals to cosine of the theta once again, and pi plus j of sine of n pi. Since this is going to be 0 for all n, not if n is not equal to 0, this will become 0. And in this waveform, we're not going to include n is equals to 0, and we're going to manipulate it further down our discussion, and how we can split the function for it to be run in MATCAD. Next is, so what's left is just this cosine and pi. To evaluate this or to simplify this further, we're going to need to convert it to trigo first, and then we simplify further. Okay, so it's going to be, so pi and then cosine n of pi over negative jn plus pi again cosine of n pi over negative jn. And almost forgot the coefficient. So next up is to, what can we do here? We're going to combine these two functions since it's the same. It's like a plus a. And then what will result maybe n pi over negative jn, the coefficients is equal. Now this can be simplified as these two will cancel, so it's going to be 1.3 cosine of n pi to denominator's negative jn. What can we do more? Maybe we can do something here. Since j is equal to 1 over negative j, maybe we can bring this up and give and have a j in our function right here. Let's see, we need to after we change this j, after we manipulated the negative j in the denominator, maybe let's see, we can multiply 1 in terms of j over j. So this is going to be n, and we will have the j there. And then if we actually this is good. This is we don't need to multiply this. This is the form of c of n, or the c of n coefficient, which is going to be j times 1.3 over n times cosine of n pi. Now since this is an exponential function, we should we want to change this trigonometric form into something that's not trigo, right? So cosine n pi is actually equals to negative 1 raised to n. This is because cosine, any number, any positive integer or negative, if you input it here in this function and you evaluate it, it won't matter how much or how many or what is the value of it. The only thing that will matter in this function is if n is even or odd, and if n is even, then it will result into 1, and then if it's odd, it's going to be a negative 1. Let's say if n is 2, this will become a negative 1, and if it's 3, this will obviously become a negative 1. So we can change this cosine function into that term, which will result in a much neater equation for the exponential form of the Fourier series. Raised to n. So that is our c of n coefficient. Now we can complete the formula, right? Because we only need one coefficient here, so it's going to be you make rho t integral of infinity from negative infinity. Our c of n is actually j times 1.3 over n, then negative 1 raised to n. times e raised to j and t. And that's the full complex or the exponential form of the Fourier series. Now we'd like to input this in MathCAD, and we can see right here, right, where j is 1i. Of course we want to call that, and it's not the same. You can see in this MathCAD form, we did something, we manipulated the summation part because we want to avoid the part where it will divide into zero. That's why we will remove the zero from the summation of negative infinity to infinity. In this case, it's n to n because MathCAD cannot, of course, nothing can compute real infinity. So we're going to just replace infinity with an extremely high number. So how do we achieve this form in so that we can input this exponential Fourier series in MathCAD to plot it for us to see the plot, right? So what we'll do is what we'll do now is to split the sum into three parts: the negative integers, the zero, and the positive integers. How that this it will look like this. So u of t is equals to first summation of the negatives. So this will be from n equals to negative infinity to negative 1, right? And then our c of n, and then the exponential function. Now we'll have the zero coefficients, or the c of o, c naught, which is e raised to j times 0 times t, and then plus we'll start from 1 to infinity now, and then c of n once again e raised to j n of t. So in this form, we can now input it in MathCAD, and this is going to be our DC component. This is DC. This is the negative and the positive. So what I mean by negative and positive are negative and positive integers, or n, right? So why is this 0 DC? So if we repeat the computation, because from the first problem, right, from the trigonometric form, DC is, I don't know, I mean that this is CO is all similar to A naught, or the DC component. So its formula is CO is equals to 1 over 2 pi integral of negative pi of f of t dt. And we know that that will result to the DC component as in this part of A naught. As you can see, it's completely similar. So we can say that the zero component here is just the average voltage of the waveform, or the DC component, is equals to V average. So that's why in the MathCAD, as you can see here, I used V average plus the negative components and then the positive components. By the way, my n here is around 10,000 or to 100,000, like that. It's a very large number. And this is the output waveform. It's completely similar to the first geometric waveform. So next, how about we dive into the compact form of the Fourier series, right? So the compact form is a little bit different from the other because it has phase in it. It has a phase. So the general form for the compact trigo is first is the DC, of course, plus. So this is the summation from n equals 1 to infinity of Cn cosine of nt plus some phase Fn. So that is the compact trigonometric form. In this form, we're still going to use the elements that we got from the wave, like our DC is equals to 0.7, right? Our A of n is 0, and B of n, of course. The sine coefficient, the cosine and then the sine coefficient, we're going to use those in this form. So we can say that this is cosine of n pi. And first, since we already have the DC component, it is equal to that 0.7. And then now we're going to solve for Cn. Now, in compact trigo form, Cn is actually Pythagorean. So we're going to use the Pythagorean theorem, where the formula is an squared, square root of an squared plus bn squared. Since this is 0, we can neglect that and we can just cancel out the square and square root. So Cn is equals to absolute value of Bn, right? And since Bn is equals to this term right here, so we're going to use this function 6 n of cosine of n pi. So since it's absolute value, we can just remove this negative sign. So it's just 2.6 over n cosine of n pi. Now, we can actually remove the n pi part. Why? Because, as I've said within the exponential function, the cosine of n pi will always resolve to positive or negative 1 if n is not 0, right? So, if the cosine of n pi will always result to a positive or negative 1 for all integers, non-negative integers and non-zero integers, this will always result in positive or negative 1. And then, since it's positive or negative 1, this won't matter since the whole function is in absolute value. Whether it's negative, it's always going to be positive. So we can just neglect this function, or this term. We can just neglect this part. And then now we have Cn is equals to 2.6 over n. Now that's our coefficient. Let's now solve for the phase. Now this is more on the phase of the compact trigo function, or Fourier series rather, is a little bit tricky because in our part in my circumstance in the Sawtooth waveform, the phase is equals to arctangent is equals to arctangent of negative bn over an. Since our an is 0, so it's going to be something like this. we already know that this is going to equal to infinity. And since we have a bn, if we make a negative bn right here, it's just going to be a positive reflection of the original term, right? Going to be like that. Negative bn is something like this. So since this will always become infinity, it will become a positive or a negative infinity. It will become a positive or negative infinity depending on what the n is, right? Since we're evaluating this function from n is equals to 1 to infinity, so it's all positive integers. What we're once again concerned here is if n is even, or if n is odd. So that's what we are concerned about here. So you can absolutely neglect this part of the b of n and just focus on cosine and pi, right? Also, for the arctangent part, the arctangent of infinity is the arctangent of infinity is going to be 90 degrees. 90 degrees. Since we're going to have plus minus here, it's going to plus minus 90 degrees. So we can say that the phase of the sawtooth function in this combined trigo form will always be 90 degrees. That's the magnitude. What we're going to, so it's going to be vertical, always vertical, right? So what we're concerned about is the operation of the said the sign of the said magnitude. Like, this is positive or negative. How are we going to accomplish that? Since 90 degrees is equals to pi over 2, now we need a function that will always generate negative 1 or 1, like this cosine and pi. We can actually just put here cosine and it will work. That will be our phase, right? Because if n is what do you call this, if n is positive, then this pi over 2, no, I mean if n is even, right? If n is even, then this pi over 2 will become a positive pi over 2. This will become positive 1. And if n is odd, this will become a negative 90 degrees, right? So that's our phase. Since we only have two possible results for our phase, which is tangent of negative or tangent of arctangent of positive or arctangent of negative infinity. I mean, um, we can use this term right here because we only need to determine the direction or the sign of the 90 degrees magnitude. So we can say that the phase of n is equals to pi over 2 times this function. We're going to make it a little bit neater. So we're going to use the other form, negative 1 raised to n. Now, with this form, we have now the important parts, the phase of n, and then the c of n, which is the coefficient of the cosine function, right? So we can now complete the general formula specifically to our waveform. So it's going to be the DC component first, C of O, which is 0.7 plus summation starting from all positive integers to infinity. And then next up is our C of n, which is going to be 2.6 over n is our coefficient, and then the cosine function with its angle n of t plus some phase of pi over 2 times negative 1 raised to n. So that is the complete, this is the complete form of the compact trigoform. If we would like to, if we input this in MathCAD, it should have the exact waveform, right? So as you can see, it has the exact waveform. And by the way, in this part of the exponential, I forgot to mention that we use the real function here, right here. This is the u of t. We evaluated this function in the t time domain, and then we use real because this function will output some imaginary parts, and we would only like to plot the real parts, so we use the real function or RE function. And that's the three forms of the Fourier series for this Sawtooth. To summarize it once again, we used what we call PUT, what we call a PUT relaxation circuit. I used the PUT relaxation circuit to generate this waveform right here. As you can see, you have a 10 nanofarad capacitor as our output, or where we're measuring the output from, and then a 9 volts source with various resistors. So thank you, and that's all for today.
Ako na siya, boss. So this circuit uses a Darlington pair to discharge a capacitor, a 10 nanofarad capacitor, supplied by a PNP transistor in a constant current voltage, constant current source configuration. So I used 2N2907 PNP transistor and a 2N3904 NPN transistor for the Darlington pair. Both have betas of around 100 to 300 of value, and then general purpose PNP transistor for the constant current source. The waveform is exactly the same as the simulation.